All right, let's kick off this explainer by confronting a pretty harsh truth in AI engineering right now. Our underlying models, they've gotten incredibly good at reasoning. But here's the catch. Reasoning without the right context is just expensive hallucination. Without proper memory infrastructure, these seemingly intelligent agents are often just confidently guessing. And frankly, that is a massive roadblock when you're trying to deploy reliable AI.
Welcome. Today, we're diving into a truly fascinating journey, the evolution of the artificial brain. We're going to look closely at exactly why traditional flat vector databases are totally failing as long-term memory for AI agents, and how brand new, biologically inspired systems are finally fixing this amnesia to enable true, lifelong learning. Here's our roadmap for today. We'll cover the agent memory crisis, the 4 types of memory, hierarchical memory architectures, knowledge graphs versus vectors, biological memory consolidation, and finally building production-ready agents. Let's get right into it.
Starting off with Section 1, the agent memory crisis.
So what's actually going wrong when we try to scale current deployments past simple toy examples? Well, you hit what I like to call the messy desk problem. Because these flat systems lack a persistent shared state, you get things like context clash. Imagine an agent retrieving an old shipping address and a new one at the exact same time, basically forcing it to guess. Or even worse, context poisoning, where a hallucination is stored, retrieved, and then used to justify a completely new faulty decision. Those errors just compound in this endless feedback loop until the entire workflow is derailed.
And here is the absolute crucial takeaway. Semantic similarity does not equal relevance. Just because a database finds, say, 10,000 memories mathematically related to customer shipping inquiries, well, that doesn't mean it'll pull the one specific conversation from 3 weeks ago that you actually need to solve today's ticket. Broad similarity searches simply don't cut it when precision is on the line.
Which brings us to Section 2, the 4 types of memory. To fix this amnesiac behavior, developers are actually looking straight at human psychology to give AI a sense of time and continuity. First up, we have working memory. Think of this as the immediate short-term state of the agent during a workflow execution. It's holding the current conversation, the recent tool outputs. It's incredibly fast, but it's entirely temporary. The second that interaction is over, this information just vanishes unless the system is actively programmed to save it. Next is episodic memory. Now, this one requires true persistence and checkpointing. It's the storage of specific past experiences while preserving the actual sequence of events. This is the exact capability that allows a customer service bot to remember that you, the user it's talking to today, are the exact same person who asked about a refund last Tuesday. It basically gives the agent a localized history of what happened and when. Then there's semantic memory. While episodic memory tracks what happened, semantic memory tracks what is absolutely true. It's this persistent knowledge base of factual truths that are completely independent of specific time-based events. Picture a medical assistant referencing fixed disease information and drug interactions. That right there is semantic memory at work. And finally, procedural memory. By encoding validated skills and action sequences, agents start operating almost like dynamic state machines. They execute complex workflow designs automatically, which means they can perform multi-step tasks without having to re-reason through every single step from scratch. It's wild. They can literally modify their own operating rules based on accumulated feedback. Moving on to Section 3, hierarchical memory architectures. Okay, so when episodic and semantic memories scale up to millions of entries, we simply cannot rely on that messy desk anymore. We have to move from flat storage to a structured filing cabinet approach. Look at how rigid and fractured traditional memory systems are. When access patterns are hard-coded without dynamic conditional routing, the AI can't generalize across new environments. It just hits a wall very, very quickly. And that brings us to AMEM, or agentic memory. This concept is actually directly inspired by the Zettelkasten note-taking method. The agent autonomously constructs these interconnected notes, so when new memories arrive, they trigger dynamic updates to the existing ones. This allows the entire memory structure to continuously refine its graph execution and deepen its understanding over time, all on its own. To navigate this massive network efficiently, architectures like HMEM use what's known as conditional routing. By cascading queries through hierarchical layers like domain, category, memory trace, and finally episode, the system dynamically prunes irrelevant branches instantly. Instead of comparing your query against a million files, it finds the right drawer, then the right folder. It completely avoids exhaustive searches and massively reduces computational waste. All right, Section 4, Knowledge Graphs versus Vectors.
So, what happens when factual accuracy literally has to be exact? Like, where a fuzzy semantic guess could be catastrophic. This is a massive issue in sectors like healthcare and finance. Vectors give you broad summaries based on fuzzy approximations. GraphRag, however, is built on specific nodes and edges, explicit, defined relationships. It provides multi-hop, verifiable paths, which is absolutely essential when you need high-stakes logic, compliance, and guaranteed factual accuracy.
To see why that's so powerful, let's walk through this multi-hop reasoning path. The agent identifies a condition at one node, finds a treatment at the next, but before acting, it hits an edge alert. This acts as a hard interrupt, basically checking for conflicts with other medications the patient is on. But proving its work step by step through these explicit connections, it avoids potentially lethal hallucinations and safely arrives at a logical resolution. Section 5, Biological Memory Consolidation.
Now, we are getting to probably the most cutting-edge innovation in this whole explainer, teaching AI to literally sleep on the job. This dual-store architecture, known as active dreaming memory, mimics the mammalian hippocampus by fundamentally separating how the agent processes time. During the online wake phase, it acts in the world and logs all its raw, messy, episodic failures. Then it enters an offline sleep phase loop, using compute time to consolidate those messy experiences into verified, highly generalizable semantic rules. This consolidation pipeline happens in 4 stages. But the real magic? That's in step 3, counterfactual verification. To ensure robust fault recovery, the agent literally hallucinates hypothetical test scenarios, synthetic edge cases, to test out its newly abstracted rules. It is dreaming up simulated executions to make absolutely sure its logic is bulletproof before committing it to permanent long-term memory. How cool is that? Finally, Section 6, Building Production-Ready Agents. So, how do we actually bring all these wild theories down to earth and deploy them today? The key is treating memory not as an afterthought, but as core infrastructure. Platforms like Supermemory use a strict 5-layer context stack. They orchestrate connectors, extractors, and hybrid retrieval with a temporal memory graph engine, while keeping user profiles strictly segregated to prevent data bleeding. This achieves lightning-fast recall while maintaining enterprise-grade security. And guys, the performance leap here is just staggering. On a catastrophic forgetting stress test measured after 500 episodes, standard setups retained a mere 70% of their knowledge, but an agent utilizing active dreaming memory, it retained an incredible 95%. When you look at numbers like that, you realize this isn't just an incremental update, it's a complete paradigm shift in system stability. So as we deploy these self-correcting neurosymbolic systems out into the real world, it completely redefines our relationship with software. I mean, think about it. If these agents can refine their own logic, organize their own thoughts, and literally dream up test scenarios while we sleep, what is the actual limit to their autonomous learning? It definitely leaves us with a provocative thought to ponder about the future of artificial intelligence. Thanks so much for joining me on this explainer, and I'll catch you next time.